Alright, welcome to your video lecture for Chemistry 371, Colgate University, Fall 2019, on hypothesis testing. So in the last video, you learned how to use the t-tables to calculate confidence intervals for sets of measurements where you don't know the population standard deviation. So another way that the t-tables are used is in something called hypothesis testing. And this is a scientific strategy that you will run into all the time. I almost guarantee that you have already read papers that involved hypothesis testing, but you might not have understood what they meant. So, for example, you could measure the height of our whole class, so there are 15 of us in that room when we're all together, and you could compare that to the national average for height in the US. And so, how would you know whether those two numbers were different? So, for example, compare class height to national. So the way that we would do this in chemistry, or in science in general, in biology very often, is you would use a t-test. So the first step in using a t-test is to develop two hypotheses. It's always two. So the null hypothesis we write as H naught, and then we give it a semicolon so that we're saying this is my null hypothesis. I'm going to say mu class. So the null hypothesis in this case would be that there is no difference between our class average height and the national average. So the null hypothesis is that there's no difference detectable, and the testable hypothesis is that there isn't, that there is a detectable difference, that the two averages are not the same. This is called the alternate hypothesis. So once we've developed our two hypotheses, the null hypothesis, that there's no difference between our two means, and the alternate hypothesis, where there is a difference between the means, the next thing that we're going to do is we're going to calculate our value of t. So this is this equation that I brought up when we introduced t. And it is defined similarly to how we define z, but here we would have x bar would be our classroom average height, mu would be the national average height, s is our classroom standard deviation, and n is the number of people in our class, so that would be 15. So we would calculate a t statistic, which is a single number. The next thing that we do is that we decide on a desired level of certainty. So let's say we want to be 80% sure for our 15-person class that we are different than the national average or not. So then we go to our t-table, and we look for the row with the number of degrees of freedom we have. In this case, the number of degrees of freedom we have is actually 14. Because we have 15 people, we need to calculate the average. We lose 1 degree of freedom that way. And so our degree of freedom is 14. There is no row in this table. There are more thorough tables that would show us all of the numbers from 1 to 60. But for the purposes of this exercise, you can see that there's not that much of a difference even between 10, 15, or 20. So we're going to assume that the 14 degree of freedom confidence interval is 1.34, just like it is for the 15 degree one. So when we find that number in the table, we find the t-value for the degrees of freedom we have and the certainty level that we want, and then that becomes our t-crit. So that's steps 1 through 3. We've developed hypotheses, calculated the statistic for our data, looked up what the expected variability for that number of observations would be based on the table of t-values. And then step 4 we compare our calculated t to t-crit. So in this case, our hypothesis is just that our alternate hypothesis is that there is a difference in the averages. So if the absolute value of your calculated t, you'll notice that if your average height is less than the national average, you can wind up with a negative value for t. If our average height is higher than the national average, we'll wind up with positive values for t. So the absolute value of t, if it is greater than t-crit, that means that the variability that we observe, or the difference between our data set and the national average, is bigger than the expected variability at the confidence limit that we've chosen. So that allows us to reject the null hypothesis. At the confidence level we've chosen. So I'll note that this test is called a two-tailed test. It is simply testing for difference. So it tests for difference, but it doesn't test for which direction that difference is in. If you want to test direction, and you should only do this if you have a reason to expect that one of your data sets would be statistically different in a measure in a certain direction. For example, if you're testing a new medical test, you might want to check whether it is better than the old one, and you wouldn't care. So this is a two-tailed test. It tests for difference, but it doesn't test for direction. If you want to test for direction, then you can use a one-tailed test. In general, you should only do this if there's a reason for you to expect that your data would lead to a directionality. If you have a solid hypothesis for the fact that you think that your measured set should be higher or lower than the average of the larger set. But to test for direction, you use a one-tailed test. So in that case, instead of looking at the absolute value of t and as it compares to t-crit, if x is statistically significantly greater than u, then t should be greater than t-crit. So we remove the absolute values. We expect this to be a positive difference. We expect t to be a positive number, and it has to be bigger than t-crit for us to reject the null hypothesis. If x is less than mu, then we would expect t to be less than negative t-crit. But in general, you probably want to be using two-tailed tests in most cases, because the one-tailed tests will totally ignore a difference that happens to be in a direction that you didn't expect. So the last thing to consider when you're doing hypothesis testing is what kinds of errors you can make and what kinds of errors you are better able to tolerate. So there are two ways to make a mistake with your hypothesis test. First, you can reject the null hypothesis when it's true. So that would be a false positive. Or you can accept the null hypothesis when it's false, and that's a false negative. So higher confidence limits will minimize false positives in that you need to be more certain to reject the null hypothesis under those scenarios. And lower confidence limits will minimize the false negatives, but will also allow you to catch more cases of statistically significant difference. So your choice of confidence level depends on what kind of error you are better able to tolerate. So for example, if you're talking about a test where the risk of, let's say you're testing a medical thing and the test that you're using is fast and cheap, but there's a better test that's more accurate, more definitive, then you would want to tolerate lots of false positives. You would want to pick a lower confidence limit because you want to catch everybody possible who would fall into that statistically different category, and you want them to get the second test. Once they get the second test, the false positives get caught and those people go on with their lives. But the screening tool is the most effective if you actually choose a lower confidence limit. On the other hand, if you're writing a scientific paper and you want to state your certainty that you have detected a difference between drug A and drug B, you want to choose a higher confidence limit because that will make your findings appear more robust. And then the final thing that I'll say, in this class we're mostly going to be dealing in confidence intervals, but I'll say that significance levels, P, are completely tied to all of this. So when people talk about p-values, what they mean is the likelihood that random variability led to the observed outcome. So in our example, where we chose an 80% confidence interval for testing whether our class's height is statistically different than the national average, our p there would be 0.2. So then if we have detected a difference, we would have to say that there is at least a 20% chance that natural statistics has led us to detect that difference when it wasn't there. So that's what the p-value means. So that's why in papers you typically see p of less than 0.05. That implies a confidence limit and what they're saying by that is that there is less than a 5% chance that natural variability has led to the observation we've come up with. And so that is how medical studies will report robustness of their conclusions. And I think probably the largest p you would see is a 0.05, and frequently you would see a 0.01 or even a 0.005 to imply greater and greater levels of statistical certainty that the observed difference is real.